This is Prachi Gupta. This is my video recording of all my collabs for this assignment. Write basic neural network using NumPy, Keras, and PyTorch. There are total five collabs A, B, C, D, E has to create in the assignment. I have created all the collabs and I have created a Git repo by this name, neural network using NumPy, Keras, and PyTorch. Here I have this collabs folder where I have uploaded all my collab files. I can show by opening. So here I have uploaded all my collab files. I'll create one video URL document here which will contain the URL for this recording. Also I'll include the URL in the readme file also before submitting. So let's move ahead with our collab demos. I'll just go to first collab. So in the first part of the assignment we were asked to create a collab from NumPy only, from like we have to create a 3-layer deep neural network from non-linear regression using a proper non-linear activation function and proper number of hidden layer neurons. Also we had to show the result, loss, epoch training, and the final output. So we have to do manual back propagation and chain rule based gradient propagation. So let's see how I have done it. This is my collab A. So first we start by setting up our environment with NumPy TensorFlows. We'll use specifically for its efficient INSUM operation. TensorFlow has that INSUM operation that is very useful, so that we will use in future, and that's why we have imported TensorFlow. We are setting up random seed to 42 uh, to ensure the reproducibility, to ensure our synthetic data and weight initialize remain consistent. Once that is done, our data set is generated from a complex nonlinear equation involving sines and cosines across three input variables. We normalize both input and the target y to ensure stable training, which is critical processing step for the deep learning. So we have generated a random input data, and then we have combined input matrix, and then we have created this nonlinear function using sine and cosine, and this is the data set that we have generated. Once the data set is generated, we are normalizing the input output for the beta trainings. Here we are taking the mean, standard deviation, normalization, everything we are doing. Once that is done, we have defined a 3-layer architecture, that is 3 is to 10 is to 8 is to 1. This is, so 3 is the input size, 10 is the hidden layer 1's size, there will be 10 neurons in the first hidden layer, 8 neurons in the second hidden layer, and the output variable will be 1. So this is how our architecture we have defined. Along with that, we are using ReLU and 10H activation functions. The forward pass is implemented using before moving to the forward pass, let's see, here we are initializing the weights and biases for layer 1, and then layer 2, and then layer 3. So layer 1 is our input to hidden layer, and then hidden 1 layer 2, hidden 2 layer will be our layer 2, and layer 3 will be hidden layer 2 output. So this is how we are defining our layers 1, 2, 3. Then we have defined a ReLU activation function, ReLU derivative, and then we have defined 10H activation function with 10H derivative. We have also defined this linear activation function and linear derivatives. So this is our function definition part. Once that is done, we will define the forward pass. The forward pass is implemented using the TF INSUM, which provides a very expressive way to handle matrix multiplication. So this is our INSUM functions that we have defined for each layer, and once that is done, so the first hidden layer we are using ReLU in the INSUM. For the second hidden layer we are using the 10H, and the third hidden layer we are using the linear function. So once that is done, we are storing the immediate values for the back propagation, and this is how we have defined the forward propagation using TensorFlow Einstein. Once that is done, we will implement manual back propagation using the chain rule to compute gradients for every weight and bias. So this is how we are defining it. Backward pass using chain rule and compute gradient. So we have get the cached values from the forward pass that we have stored here. So we are getting that cache value. Once that we have all those values, first we will go through layer 3 gradient. So we'll do the derivative of MSE loss linear activation, and then we will apply Einstein sum for, and then do the sum of the data. Then we will do the layer 2 gradient similarly using the 10h derivative, and then we will do the layer 1 gradient using the ReLU derivative. So, and we will store the gradients, and this is how we have defined the back propagation using the function. After that, I have done this training loops, training epochs. We have defined 5000, and these are the starting training, and then we are doing training epoch, and we will do forward propagation, then we will compute the loss, and then we will do backward propagation, and then we will keep updating our weights and biases for each epoch, and then we will print the values for each epoch cycle. So this is how we have done, and this is our final train loss after training completed. So once that is done, after the training, we will visualize the loss curve, and we then we will from the convergence. So we have plotted our loss curve. Once that is done, we will do the we'll also calculate the r square for achieving over 0.92 to compare our first 10 predictions against the actual values. So let's see. So the reduction is 92%, the loss reduction. Now we have this final prediction. We will calculate the r squared score. So then we will compare the r squared score with our first time prediction and again the actual values. So this is our r square value, and then the first 10 predictions. This is the actual value, this is the predicted value, and this is the error that it has, the error amount. So this is the output of that. And to visualize the 3D inputs and 1D output, we use PCA to reduce the input to two principal component, and this allows us to create a 4D plot where height and color represent actual versus predicted values. So we will define here PCA dimensionalities, and then we will create a 4D plot for where two dimensions will be the spatial dimensions. One height dimension will be the actual, and one color dimension will be the predicted. So let's plot it, and then we will see. So these are our actual values, and these are our network predicted values. So this is how we can compare, and this is a quick summary of what we have done. We have 3-layer deep neural network with this data set equation, 1000 samples. We have done 5000 epochs, our learning rate, initial loss, final loss, and the loss reduction rate we have given. This is our performance, and this is our key implemented features. We'll also now visualize the networks and weight gradients. So we are using our hidden layers to print the gradients, and we will generate a new test data that is unseen during the training, and then we will test our model on those data. So let's see how our model performs. So we have this normalized text data, and then we will make predictions on the test data, and then we will calculate the r square value here, and this is the output of it. We can see the r square is 0.92, and the mean absolute error is 0.36. So we will again create a scatter plot to compare the predictions and the actual values. So here we are using the training set, and here we are using the test set to create the scatter plots. So this is our training set, and this is the r square value, and this is the test set, and this is our r square value. So r square value is almost equal, and the correlations also we can see it's almost 0.96 and 0.95. So we'll analyze the prediction errors. So let's see. What we'll do is we will plot the training errors on the histogram, we will plot the test errors on the histogram, and then we will plot the training residuals and the test residuals, and then we will compare all of them. So we can see this is the training error distribution, this is the test error distribution, this is the test residual plot, and this is the training residual plot. And we can see the training mean error was this much, and test mean error, training standard error, and then test standard deviation error. So this is the assignment complete report we have, whatever we have done, and this is for the part 1 of the assignment. I'll upload another video for part 2 of this assignment. Thank you so much.